When German engineers at the Kummersdorf testing facility first conducted a detailed examination of a captured American M4 Sherman tank, their conclusions represented an unexpected admission of enemy superiority in an area Germany had always prided itself on: engineering excellence. This wasn't merely an analysis of opposing hardware. It was a collision between two diametrically opposed philosophies of tank design: German obsession with technical perfection versus American pragmatism focused on mass production. The story of German testing of the Sherman reveals one of World War II's greatest ironies. A tank frequently criticized for inadequate armor and firepower proved to be a model of engineering reliability that the Germans never managed to achieve in their own designs. While German tanks like the Tiger and Panther captured imaginations with their raw power and technological sophistication, the humble Sherman demonstrated something far more valuable in total war: the ability to actually work consistently under the harshest conditions imaginable. This examination of German test reports, technical assessments, and post-war interviews with engineers reveals a fascinating narrative about what actually wins wars. Not necessarily the most advanced weapon, but the one that shows up, functions reliably, and can be maintained by ordinary soldiers under combat conditions. Kummersdorf, located approximately 60 kilometers south of Berlin, had served as the German Army's primary testing ground since 1875. By World War I's outbreak, it had evolved into an enormous complex where all types of military equipment underwent rigorous evaluation, from small arms to the heaviest tanks. This was where captured Allied equipment was sent for systematic study. Beginning in 1943, when American forces entered combat in North Africa and Italy, captured Shermans began arriving at Kummersdorf. Early M4A1 models with cast hulls were taken from the 1st U.S. Armored Division in Tunisia and shipped to Germany for comprehensive analysis. Surviving photographs show these tanks bearing German markings indicating armor thickness and angles, clear evidence of methodical examination. The German testing protocol was exhaustive. Engineers fired various caliber weapons at the armor from different ranges and angles. They completely disassembled powertrains, tested transmissions under load, examined crew ergonomics, and evaluated optical equipment. Every component was documented, measured, and compared against German equivalents. The goal wasn't just to understand the enemy's capabilities, but to identify potential improvements for German designs and to discover weaknesses that could be exploited in combat. The testing facility maintained detailed records, including firing trials against captured armor, endurance runs on test tracks, and mechanical stress tests. Some Shermans were run until failure to establish mean time between breakdowns, data that would prove particularly revealing. When German mechanics first opened the engine compartment of a Sherman, they were struck not by technical sophistication, but by its opposite: elegant simplicity. The Continental R975 radial aircraft engine, in early models, or the Ford GAAV8 in later variants, was easily accessible, with clear service points and straightforward maintenance procedures. German tankers were accustomed to the Maybach engines in Panthers and Tigers, precision-built power plants that delivered impressive performance but required specialized tools and extensive training to service properly. One German engineer's report noted with surprise that the Sherman's engine could be removed and replaced by an average crew in a matter of hours using basic tools. This stood in stark contrast to German tanks, where engine removal was a major undertaking requiring specialized equipment, workshops, and highly trained personnel. A Panther's engine change typically required a crane and could take days. A Sherman crew could accomplish the same task in the field. The transmission told a similar story. German engineers examining the Sherman's transmission and final drives found them robust, if unsophisticated, by their standards. The components were larger and heavier than German engineers would have designed them, seemingly over-engineered for the power they transmitted. This crude approach puzzled the Germans initially. Why use so much material when more elegant solutions existed? The answer became apparent during endurance testing. While German transmissions were marvels of compact design, they operated near their maximum stress tolerances, making them vulnerable to failure under sustained use or battlefield damage. The Sherman's overbuilt transmission, meanwhile, operated well within its design limits, providing an enormous reliability margin. It could tolerate battlefield abuse, imperfect maintenance, and sustained operation that would destroy more refined German units. German engineers also noted the Sherman's use of standardized parts and modular design. Components were interchangeable not just between tanks of the same model, but often across different Sherman variants. This standardization extended to tools. A limited set of standard wrenches and screwdrivers could service most of the tank. German tanks, conversely, often required model-specific tools and components, with even minor variations requiring different parts. The most significant German assessment came after extensive field testing. One report, compiled after running several captured Shermans through hundreds of kilometers of varied terrain and combat simulations, contained a statement that must have been difficult for proud German engineers to write. The Sherman demonstrated operational reliability that exceeded anything in the German arsenal. The numbers were damning. German testing showed that a Sherman could typically operate for 150 to 200 hours between major mechanical failures. A Panther, by comparison, averaged around 150 kilometers before requiring major repairs in its early production, roughly 10 to 15 hours of operation. Even later, improved Panthers rarely matched the Sherman's reliability. The Tiger was worse, with chronic problems in its complex overlapping wheel system, transmission, and engine. German engineers identified several factors behind the Sherman's superior reliability: tolerances and manufacturing. American factories built Sherman components with looser tolerances than German precision manufacturing. Counterintuitively, this improved reliability. Tighter tolerances mean components are more susceptible to damage from dirt, debris, or thermal expansion. The Sherman's looser design philosophy meant it continued functioning even when parts weren't perfect, crucial in field conditions where precision maintenance was impossible. Accessibility. Every major component in the Sherman was designed for easy access and replacement. The Germans noted that even unskilled personnel could perform major repairs with minimal training. German tanks required specialist mechanics. The Sherman could be maintained by average soldiers. Durability under stress. German engineers subjected captured Shermans to abuse tests, running them over rough terrain, operating them in dust and mud, deliberately neglecting maintenance schedules. The Shermans continued functioning far longer than German tanks would have under similar treatment. Engine reliability. The radial and V8 engines in Shermans were derived from proven civilian and aircraft designs with thousands of hours of operational testing. German Maybach engines, while powerful, were essentially custom designs without extensive pre-war development. This showed in their reliability statistics. One German report stated bluntly, "The American tank's mechanical reliability is superior to our own designs." While individual components may lack the sophistication of German engineering, the overall system demonstrates a level of dependability we have not achieved. The German analysis of the Sherman inadvertently revealed a fundamental philosophical divide between German and American approaches to military engineering. This divide would ultimately prove decisive in the war's outcome. German engineering tradition emphasized technical excellence, precision, and sophisticated solutions. This approach produced some of the war's most impressive individual vehicles: the Tiger's fearsome 88mm gun and heavy armor, the Panther's excellent balance of firepower, protection, and mobility. The Ferdinand tank destroyer's massive gun and armor. These were engineering masterpieces that reflected centuries of German technical achievement. However, this perfectionist approach created serious problems in total war. Production complexity. German tanks were difficult and time-consuming to produce. A Tiger required approximately 300,000 man-hours to manufacture. A Sherman needed about 10,000 man-hours. This meant that even when German factories operated at full capacity, they couldn't produce vehicles in quantities needed for a multi-front war. Maintenance requirements. German tanks needed frequent, specialized maintenance. They required trained mechanics, specific tools, and regular access to workshops. The Sherman could be maintained by its crew in the field with basic tools. Supply chain complexity. German tanks used numerous custom components that weren't interchangeable between models. This created logistical nightmares. Every tank model needed its own spare parts pipeline. The Sherman standardization meant a single set of spare parts could service entire armored divisions. Reliability trade-offs. Pushing for maximum performance often meant operating components near their stress limits. German tanks achieved impressive specifications, but at the cost of frequent breakdowns. American engineering, by contrast, prioritized different values: reliability, ease of production, maintainability, and logistical simplicity. The Sherman wasn't trying to be the best tank in a one-on-one duel. It was designed to be produced by the tens of thousands, shipped worldwide, maintained by average crews, and keep fighting despite imperfect conditions. German engineers understood the technical merits of this approach, even as they recognized it contradicted their engineering tradition. One engineer noted in a report, "The American tank is not built to our standards of precision, yet it achieves its purpose more effectively than our more sophisticated designs." This suggests we may have been pursuing the wrong objectives. German engineers compiled detailed assessments of various Sherman systems, revealing both admiration and frustration. Suspension system. The Sherman's vertical volute. Spring suspension, VVSS, was considered crude by German standards. The Germans had moved to more sophisticated torsion bar systems. However, testing revealed the VVSS was remarkably durable, easy to repair, and provided adequate performance. Damaged springs could be replaced in the field without specialized equipment. German torsion bar systems, while providing better ride quality, were far more difficult to repair when damaged. Tracks. Sherman tracks were simpler than German designs, lacking the sophisticated rubber pads and complex attachment systems of Panther tracks. Yet, they were more reliable, easier to replace, and adequate for the task. German reports noted approvingly that Sherman crews could change tracks in the field, something that often required recovery vehicles for German tanks. Armor quality. German metallurgists found American armor plate to be of excellent quality, with consistent hardness throughout. While not as thick as German heavy tank armor, it was well sloped, in later models, and manufactured to high standards. The welding quality particularly impressed German inspectors. American welds were clean, consistent, and strong. Optics and sights. This was one area where Germans maintained clear superiority. German optical instruments were significantly better than American equivalents. Sherman periscopes and gun sights were considered adequate but not exceptional. However, Germans noted that American optics were much easier to replace. Damaged sights could be swapped out quickly, while German precision optics required careful adjustment after installation. Ergonomics. German engineers were surprised by the spacious crew compartment. German tanks, designed to minimize profile and maximize armor, were notoriously cramped. The Sherman provided significantly more space, reducing crew fatigue and improving combat effectiveness during prolonged operations. The powered turret traverse also impressed the Germans. Most German tanks still used manual traverse, requiring significant physical effort from the gunner. Ammunition storage. Early Shermans had a serious vulnerability. Ammunition stored in sponsons was prone to catastrophic fires when penetrated. German tests confirmed this weakness, and tactical doctrine was developed to exploit it. However, Germans also noted that later, Sherman models with wet ammunition storage, surrounded by water jackets, dramatically reduced this vulnerability. The German report noted, the Americans identified a critical flaw and implemented a solution across their entire tank fleet within months, a feat of production coordination we could not match. German technical reports couldn't ignore the strategic implications of Sherman's design philosophy. By 1944, as the Western Allies prepared for the Normandy invasion, the production numbers told a stark story. The United States produced approximately 49,000 Sherman tanks during the war. Germany produced about 6,000 Panthers and 1,350 Tigers, their primary medium and heavy tanks. Even including all German tank and assault gun production, the numbers didn't approach Allied output. German engineers recognized that even if a Panther could defeat 3 or 4 Shermans in combat, a claim often made but seldom achieved in practice, the Americans could simply produce more Shermans faster than Germany could destroy them. Moreover, Sherman reliability meant more tanks remained operational. German armored divisions frequently had 30 to 50% of their tanks under repair. American armored divisions typically maintained 80 to 90% operational readiness. One German report calculated that accounting for production time, transportation to the front, maintenance requirements, and operational availability, a single Sherman represented more combat power over time than a Panther, despite the Panther's superior gun and armor. This was because the Sherman was more likely to be available when needed, more likely to reach the battlefield without breakdown, and more likely to remain operational throughout a campaign. The irony of German testing was that while engineers recognized Sherman's virtues, this knowledge rarely translated into action. German production philosophy was too deeply entrenched to change, even when evidence mounted that a different approach was needed. Some attempts were made to apply lessons from the Sherman. The development of the Panther II and Tiger II included some efforts at standardization and simplified maintenance. However, these remained far more complex than American designs. The fundamental German belief that technical superiority would prevail prevented the radical simplification that would have been necessary to match American production efficiency. There were also military cultural factors. German tank crews took pride in their sophisticated machines. Officers viewed tank warfare through the lens of individual vehicle superiority rather than operational availability. The idea of deliberately downgrading to simpler, more reliable designs conflicted with German military tradition and self-image. By the time German engineers fully appreciated the Sherman's design philosophy, it was too late. Germany's industrial capacity was being destroyed by Allied bombing, raw materials were increasingly scarce, and the skilled workforce was depleted. Even if German leadership had wanted to switch to Sherman-style mass production, they lacked the resources and time to make the transition. After the war, some German tank designers reflected on the lessons of the Sherman. Ferdinand Porsche, who had designed various German armored vehicles, reportedly said that if he could redesign German tanks with wartime knowledge, he would have prioritized reliability and production efficiency over technical sophistication. Otto Carius, a famous German tank ace, wrote in his memoirs about the frustration of mechanical breakdowns, "Give me a Sherman's reliability in a Tiger's chassis, and we would have been unstoppable." This comment, from a man who had knocked out hundreds of Allied tanks, reveals the respect German tankers developed for American engineering practicality. American engineers, for their part, recognized the Sherman's limitations. Its armor and gun were adequate in 1942, but increasingly marginal by 1944 to 45. However, The basic chassis proved remarkably adaptable. Variants included tank destroyers, recovery vehicles, self-propelled artillery, rocket launchers, mine clearers, and even bridge layers. This versatility, another product of the original design's simplicity and reliability, extended the Sherman's service life decades beyond World War II. The German technical assessment of the Sherman ultimately vindicated American engineering philosophy. While German tanks were individually impressive, the Sherman proved that reliability, maintainability, and producibility were more important than raw performance specifications. This lesson extended beyond tanks. The same philosophy appeared in American aircraft, the reliable P-47 versus the sophisticated but troublesome Me-262. Trucks, the ubiquitous Deuce and a half versus German semi-specialized transport, and even small arms, the simple M1 Garand versus the more sophisticated but less reliable German rifles. German engineers at Kummersdorf recognized what their leadership could not fully accept. In industrial warfare, the weapon that works consistently beats the weapon that works perfectly, but rarely. The Sherman wasn't the best tank in World War II by traditional metrics of firepower, armor, or mobility. But it might have been the best weapon system, considering all factors that actually matter in war. The admission by German engineers that they had never built reliability like this wasn't just a technical judgment. It was in recognition that Germany had been fighting the wrong engineering war. They had been building masterpieces when they needed to build tools. The Sherman was a tool, and like any good tool, its greatest virtue was that when you needed it to work, it did. The story of German engineers testing the Sherman and admitting its superior reliability illuminates a broader truth about engineering in wartime. Theoretical excellence matters less than practical effectiveness. The Sherman's design team, working with less sophisticated manufacturing technology than German engineers, created something more valuable than a technically superior tank. They created a reliable war machine that ordinary soldiers could keep running under the worst conditions imaginable. This wasn't an accident or a lucky break. It was the result of deliberate design choices that prioritized different values than those prized by German engineering tradition. Every crude component, every over-engineered system, every unsophisticated solution in the Sherman represented a conscious decision to favor reliability and maintainability over performance and elegance. The German testing reports, buried in archives until after the war, show engineers struggling with cognitive dissonance. How could this relatively simple American design outperform their sophisticated masterpieces in such a critical metric? The answer was that American engineers had asked different questions. Not, how can we make the best tank? But, how can we make a tank that will actually help win the war? That question led to the Sherman, a tank that German engineers admitted they couldn't match for reliability, and that distinction helped change the course of history. Sometimes the greatest engineering achievement isn't building something perfect, it's building something that actually works when it matters most. Beyond the mechanical assessments, German analysts examined another crucial aspect where the Sherman excelled: its relationship with its crew. This dimension of tank design revealed yet another area where American pragmatism triumphed over German technical sophistication. German reports noted that Sherman crews could be trained to operational proficiency significantly faster than their German counterparts. A German Panther crew required months of intensive training to fully master their vehicle's complex systems. The Sherman's intuitive layout and simpler controls meant crews could reach combat effectiveness in weeks. This training efficiency multiplied the tank's strategic value. America could not only produce more tanks faster, but could also produce qualified crews faster. The Sherman's interior design reflected careful attention to crew ergonomics that German engineers found remarkable. The fighting compartment provided enough space for crew members to move without interfering with each other during combat operations. German tanks, designed to minimize external dimensions, forced crews into cramped positions that caused fatigue during extended operations. One German report observed, "American tankers can fight effectively for extended periods because they are not physically exhausted by their vehicle's layout." Crew survivability was another area where German testing revealed uncomfortable truths. While early Shermans had the notorious tendency to catch fire when penetrated, earning the grim nickname Ronson among crews, after the lighter that lights first time, every time, the overall crew survival rate in Shermans was substantially higher than in German tanks. German engineers identified several reasons. The Sherman's escape hatches were larger and better positioned than those in German tanks. In testing scenarios simulating crew evacuation under fire, Sherman crews could abandon their vehicle in seconds. German tank crews, particularly in Tigers and Panthers with their heavy armor, often struggled with stiff hatches that required significant force to open, potentially fatal when the vehicle was on fire. The Sherman's ammunition storage, while vulnerable in early models, was addressed through the wet storage modification. German engineers noted this change appeared across the entire Sherman fleet with remarkable speed, demonstrating an institutional responsiveness to field feedback that Germany couldn't match. German tanks continued to have ammunition storage vulnerabilities throughout the war because implementing changes across multiple production facilities and existing vehicles proved logistically impossible. Perhaps most significantly, the Sherman's mechanical reliability meant crews were less likely to be abandoned in broken-down vehicles during combat. German tankers faced a nightmarish choice: stay with a disabled tank and try to repair it under fire, or abandon valuable equipment. Sherman crews could often perform field repairs quickly enough to remain with their units, or if abandonment was necessary, they knew recovery and repair would be feasible. This psychological factor, confidence in their equipment, translated into better crew performance and morale. German engineers examining the Sherman gradually realized they weren't just looking at a tank. They were examining an entire system of warfare that integrated production, logistics, maintenance, and combat operations into a coherent whole. This systems-level thinking represented perhaps the most profound difference between American and German approaches. The Sherman was designed from the outset with logistics in mind. Its dimensions were carefully calculated to fit within the constraints of American infrastructure. It could be transported by standard rail car, driven over typical bridges, and most crucially, shipped overseas efficiently. The tank's width was specifically limited to fit within the loading capacity of Liberty ships, the mass-produced cargo vessels that formed the backbone of Allied logistics. German tanks, by contrast, were often designed without adequate consideration for strategic mobility. The Tiger was too wide for standard railroad flat cars, requiring special transport procedures. Its weight exceeded the capacity of most bridges, forcing lengthy detours. Panthers and Tigers were regularly damaged during transport not because of enemy action, but because German infrastructure couldn't adequately support them. The Sherman's fuel efficiency also stood out in German testing. While not exceptional by civilian standards, the Sherman consumed significantly less fuel per kilometer than comparable German medium and heavy tanks. In an era when fuel was increasingly scarce for Germany, this efficiency represented an enormous strategic advantage. The Panther consumed approximately 300 liters per 100 kilometers on roads, and far more cross-country. The Sherman typically used 150 to 180 liters per 100 kilometers. This meant Sherman units could operate with longer supply lines and smaller logistical footprints. German reports documented the Sherman's air filter system with particular interest. The American tank used a sophisticated oil bath air filtration system that could function effectively even in extremely dusty conditions. This proved crucial in North Africa and later in the dusty summer conditions of France and Germany. German tanks, equipped with less effective air filters, suffered frequent engine problems when operating in dusty environments. Engines ingested dust, wearing cylinder walls and contaminating oil. The Sherman's superior filtration meant engines lasted longer under identical conditions. Parts standardization represented another logistical advantage that German engineers recognized but couldn't replicate. Sherman components were designed for interchangeability, not just within the same model, but often across different variants. An M4A1 with a Continental radial engine and an M4A3 with a Ford V8 shared numerous components: tracks, suspension parts, road wheels, transmission components, weapons, sights, and countless smaller parts. This meant a single consolidated spare parts supply could support mixed tank formations. German tank production, by contrast, created a logistical nightmare. Panthers from different factories often required different parts due to manufacturing variations. Early and late production Tigers weren't fully compatible. The Tiger I and Tiger II shared almost no components despite the name. Every German tank model represented a separate supply chain. Multiply this across assault guns, tank destroyers, and other variants, and German logistics became impossibly complex. One revealing calculation in German reports estimated that supporting 100 Sherman tanks in the field required approximately 40% of the logistical effort needed to support 100 Panthers, even when accounting for greater combat losses among the Shermans. The Shermans' reliability, ease of repair, and parts standardization more than compensated for its tactical disadvantages. German technical evaluations also examined battlefield modifications and variants, revealing another dimension of the Sherman's design genius: adaptability. The basic chassis proved remarkably versatile, spawning dozens of specialized variants that addressed specific tactical needs. The M4 chassis served as the foundation for the M10 and M36 tank destroyers, mounting more powerful guns for anti-tank work. The M7 Priest self-propelled howitzer provided mobile artillery support. The M32 tank recovery vehicle could retrieve and repair damaged tanks in the field. Specialized variants included bridge layers, mine clearers, including the fearsome Crab flail tank, flamethrower tanks, rocket launcher platforms, and even amphibious variants. This versatility stemmed directly from the Sherman's design philosophy. Its robust, over-engineered chassis could accommodate different turrets, weapons, and equipment without compromising reliability. The spacious hull and powerful engine provided margins that allowed modifications without exceeding design limits. German tanks, optimized for their specific roles, proved far less adaptable. Attempts to mount larger guns in Panthers required extensive redesign. Creating specialized variants of Tigers was prohibitively expensive. The German approach of building highly optimized vehicles for specific purposes meant they needed different platforms for different roles, multiplying production complexity. German intelligence officers observed that American armored divisions could configure task forces with the exact mix of capabilities needed for specific missions, all using variants of the same basic vehicle. This simplified training, maintenance, and logistics while providing tactical flexibility. German formations, equipped with diverse vehicles, struggled with the complexity of supporting multiple platforms simultaneously. The Sherman's adaptability extended to field modifications by combat units. Crews regularly added improvised armor, sandbags, extra machine guns, and other modifications. The tank structure was forgiving enough to accept these changes without mechanical penalties. German tanks, operating closer to their design limits, couldn't tolerate similar modifications without compromising performance or reliability. Understanding German engineers' conclusions about the Sherman requires examining the industrial context that produced it. American manufacturing capabilities in the 1940s represented a unique convergence of factors that Germany couldn't replicate regardless of design philosophy. American industry had spent decades perfecting mass production techniques, pioneered by Henry Ford's automobile assembly lines. These methods emphasized standardization, interchangeable parts, specialized machinery, and assembly line manufacturing. When applied to tank production, they enabled unprecedented output. The Chrysler Detroit Arsenal tank plant could produce a completed Sherman every hour at peak production, a rate German factories never approached for any tank. American industry also benefited from abundant resources. Steel, rubber, petroleum, rare metals, all were available in quantities that Germany couldn't match even before Allied bombing disrupted German production. This abundance allowed American engineers to design with generosity, using more material than strictly necessary to ensure reliability margins. German engineers, constrained by material shortages, had to optimize every design to minimize resource consumption, often at the cost of reliability. The geographical security of American production facilities cannot be overstated. Sherman factories operated without fear of bombing, with stable power supplies, regular component deliveries, and a workforce that wasn't being drafted or killed in bombing raids. German production facilities faced constant disruption, forcing evacuation to less efficient locations, operating with inexperienced workers, and coping with infrastructure damage. Quality control in American factories maintained consistent standards throughout production. German quality control deteriorated as the war progressed, with forced laborers and unskilled workers replacing craftsmen. This resulted in increasing variance in component quality, further undermining the reliability of sophisticated designs that required precision manufacturing. German reports occasionally touched on an intangible but crucial factor: crew confidence. Sherman crews, knowing their tank would probably start, probably get them to the objective, and probably get them home, fought differently than German tankers, who never knew when their vehicle might break down. This psychological security translated into tactical advantages. Sherman units could plan operations knowing they would likely execute them with the vehicles they started with. German units had to account for significant mechanical attrition even during approach marches. A German armored division moving 100 kilometers to battle would typically arrive with 10 to 20% of its tanks disabled by mechanical failures. An American armored division would arrive with 95% plus of its Shermans operational. Crew confidence also affected decision-making in combat. Sherman commanders could push their vehicles hard, knowing they could withstand abuse. German tankers had to balance tactical aggression against the knowledge that mechanical stress might disable their tanks, leaving them stranded. This psychological burden affected everything from tactical maneuvering to strategic planning. The German testing reports, clinical and technical in most respects, occasionally revealed frustration with this dimension. Engineers could measure horsepower, armor thickness, and mean time between failures, but quantifying the combat value of crews who trusted their equipment proved elusive. Yet this trust multiplied every other advantage the Sherman possessed. The lessons German engineers learned from testing captured Sherman's influenced post-war German armored vehicle design, though this legacy is rarely acknowledged. When West Germany began rearming in the 1950s, the Bundeswehr's tank requirements emphasized reliability and maintainability alongside firepower and protection, a notable shift from wartime priorities. The Leopard 1, West Germany's first post-war main battle tank, reflected many principles that German engineers had observed in the Sherman: emphasis on operational availability, ease of maintenance, efficient logistics, and producibility. While far more sophisticated than a Sherman, the Leopard incorporated the understanding that reliability matters more than peak performance. Globally, the Sherman's influence persisted for decades. Many nations operated Shermans into the 1970s and even 1980s, often with upgraded weapons and engines. The basic design proved so sound that it could be modernized repeatedly. Israeli Super Shermans, equipped with French 105mm guns and modern engines, remained combat effective into the 1970s, 30 years after the original design. This longevity validated everything German engineers had observed: a well-conceived design emphasizing reliability, maintainability, and adaptability could remain relevant far longer than more sophisticated but fragile alternatives. The German engineers' admission that they had never built reliability like the Sherman represents one of history's great technical compliments, made more significant by coming from experts who had every reason to defend their own work. Their testing revealed an uncomfortable truth: American engineers had solved problems German engineers hadn't fully recognized existed. The Sherman wasn't perfect. Its armor was adequate rather than exceptional. Its gun was sufficient rather than superior, and its mobility was good rather than outstanding. But it started reliably, ran dependably, could be fixed by its crew, supported by efficient logistics, produced by the thousands, crewed by rapidly trained tankers, and adapted to numerous specialized roles. In total war, these virtues mattered more than any amount of technical sophistication. The story of German engineers testing the Sherman and confronting the superiority of its reliability illuminates a profound lesson about engineering. Understanding the actual problem is more important than technical virtuosity in solving the wrong problem. American engineers understood that the problem wasn't building the best tank, but building the best weapon system for industrial warfare. That insight, translated into the humble Sherman, helped win World War II and influenced armored vehicle design for generations. Sometimes the greatest engineering achievement isn't the most impressive on paper. It's the one that actually works when everything else fails.